This is Project Team 3, MSIS 5633, Business Analytics Technologies. I'm Chase Haddikin. With me, I have Asher Floyd, Caleb Smith, and Nathan Zlomke, and our project was predicting car crash severity. So, like I said, our project was developing a machine learning model for the prediction of car crash injury severity. So the reason that this is important, obviously, is that it's impactful to a large portion of the population. Um, There are also, a lot of efficient resource allocations and safety measure implementations that are connected to that I'll go over in a second. How we did this, we utilized KNIME data analytics software, National Highway Traffic Safety Administration data, and the CRISDM methodology in order to develop our solutions. And our result, after running several K-fold cross-validated models, including XGBoost, decision tree, random forest, artificial neural networks, and logistic regression. Our chosen model was the random forest model with SMOTE, which had an accuracy of 95.4%, a sensitivity of 98.7%, and a specificity of 92.1%. Some of the next steps that the team has is that the deployment of our chosen model is beyond our project scope, and future implementations with more dimensionality reduction, some sensitivity analysis, and hyperparameter tuning is needed. So on the business understanding, on car crash injury severity, I had mentioned efficient resource allocation. So for example, do you need to place certain medical resources on highway systems for more at-risk populations? Others are, smart safety measures. So for policymakers, where can they efficiently place speed limits, traffic signs, and efficiently implement regulation around driving under the influence of drugs or alcohol? Then for auto manufacturers, how do you optimize things like adaptive cruise control systems or emergency braking systems to decrease the amount of high injury severity accidents? So we utilize the CRISDM methodology, as I kind of outlined before. First portion of this is business understanding. So how do you understand a problem and find a pathway to apply a data mining solution? Second part is data understanding. So how is the project data consolidated and initially understood? Third is data preparation. So that comprises all the activities of data transformations and cleaning before the use in any data mining modeling. The modeling step. So how can you utilize different models and experiment to find the most optimal solution for your data mining problem? Testing and evaluation, on the tail end of modeling. How do you go and choose the best model to apply to your problem? And then deployment. How do you take your model and push it out into the world to be used for good? We did use public data and analytics software KNIME. It's free and open source, low code application that uses node-based workflows. That's all I had on business understanding.
So for the data understanding part, before we jumped into the pre-processing and modeling, you needed to gain pretty clear understanding of what we were looking at data-wise. Like was mentioned earlier, we took 4 data sets from the National Highway Traffic Safety Administration. The 4 data sets that were used was accident data. This was giving us an idea of when the crash occurred, where in the roadway it happened, and how it happened. The second was the distracted database. This gave us, where the region of the crash happened, if the driver was injured in the crash, and how they were distracted, from animals, people, cell phones. The vehicle database showed us what type of the vehicle it was, car, pickup, small vehicle, how fast they were going when the crash occurred, the extent of the damage to the vehicle, and then like if the road conditions were rainy, dirty, slick, gravel roads, stuff like that. For the persons database, It gave us socio-demographic information about the person that was injured in the crash, how injured they were, ranging from not injured at all or to death. Um, it also showed the location of the vehicle, if any drugs or alcohol were involved, anything like that. For looking at the numeric variables that we used for the modeling process, we were looking at the model year, comparing it to high level injury and low level injury. So on average, older vehicles cause a higher level of injury. And then, looking at the speed limit, higher speed limits also cause higher injuries. And then overall, majority of accidents occurred going under the speed limit for both low level and high level injuries. For the nominal variables that we looked at, the categorical ones, lower towing capacity vehicles, so in general, smaller vehicles, were involved in most injured drivers. So the smaller the vehicle, the worse you were going to get injured in a wreck. Based off the data we looked at, heavier towing capacity vehicles involve the least number of injury drivers. So the bigger the vehicle, the less injured you will be on the road. Two-lane roads had the highest number of injuries overall. The more lanes that there were, the less high-level injuries were accounted for. Next, we'll go to the data preparation part. To start, we had our 4 data sets: accident, person, distracted, and vehicle. The vehicle and accident data sets were merged using an inner join method on the case number. With this, only data with matching case numbers from each data set were piled together into the combined data set. Next, with the combined data set, the person was merged with a left outer join by case number and vehicle number. What this did was only joined matches from the person file that had case number and vehicle number matching on the already combined data set. With this, 134 rows of data were deleted that did not fit the qualifications to be joined with that method. The distracted data set was then merged onto the combined one with the same left outer join by case number and vehicle number. With this, there were no excluded rows or events of data. Combined, there was 123,393 recorded crashes, and then 204 different variables that were involved in it. So once the data was merged into the combined data set, it was filtered. So the first thing that we did was only include events where the driver was injured. So doing that removed 32,825 crashes out of the data set. Next, we removed any crashes that resulted in death or no injury. We did this because we're only looking for people with injuries. And so that would remove the deaths or the non-injured people from our models. Also, there was large vehicles, semis, motorcycles, bikes, all of the above in the data that we were using. So we had to filter out those to only use common motor vehicles like cars, light pickup trucks, and stuff like that. Overall, there was a total of 105 and 34 accident results that were removed before moving on to the modeling process. Next, we went through and selected the variables down from 204 to about 40. The way we did this was using the random forest learner node in KNIME. So once the data was filtered, the variable selection occurred. So we took the 204 variables that we originally had in the combined data set and dwindled it down to about 40 to improve model performance. With this, we used the random forest learner node in KNIME to look at the variable importance of how they reacted with the injury high or low. So with that, we removed the very bottom ones that had no result variable importance to the targeted injury. And then we also used a genetic algorithm node for informed feature selection. With both of those combined, we got rid of 124 variables, cross-checked it with the dictionary before any removal, and then after that, we filtered it down to 40 by hand by referencing the data dictionary. For the data construction, every variable that we used either needed to be remade or re-engineered. The ways we did this was using the rule engine node. So a total of 12 variables were redone with the rule engine. 2 were created with a math formula node, and then 21 were binned with the numeric binner. With this, all missing values were imputed with the missing node within KNIME.
I'll take it with the modeling approach. So here's the general outline of our modeling flowchart. So highlighted in blue, you have the set-based models, and highlighted in green, you see the numerical models. So we took on 2 different approaches, which is helpful because you don't always know how your data set's going to be represented by the model. So it's best to test against a few different model types. Next slide, please. Initially, we noticed the target variable distribution was pretty imbalanced. You can see on the left that it's got a large majority class, and it's best for predictive accuracy to do some sort of balanced sampling technique. Initially, we looked at equal size sampling, and this actually didn't result in that great of accuracy. And the main issue that we had with it was that it actually works by reducing the data set. So it brings the majority sample down to the minority sample size. So we lost around 30,000 data points when doing this. And so we looked at synthetic minority oversampling technique, which we'll refer to as SMOTE. And this basically works like a KNN, K-nearest neighbor algorithm to form synthetic minority samples until the minority sample equates to the majority. We also used K-fold cross-validation for tenfolds. You can go to the next slide. So set-based models in general are models that identify patterns and relationships in the data set. They basically work by slicing and dicing to make the data more and more homogeneous by forming different rules. So the most basic form in this at least was the decision tree learner, and then there were a couple ensemble methods that we tried out. At the bottom, you can see just the basic flowchart flowing from k-fold, tenfolds to the decision tree and onwards. From there, you can go to the next slide. Here's an example of the split criteria for decision tree. So if you look at the bottom left, you see vehicle age, and decision tree decided that there was a split at the 5-year mark. This is similar to what Caleb mentioned, that vehicles that were older typically had higher injuries associated with them. So yeah, it made a split there. And then to the right side, you see travel speed. Another association it made is that accidents that occurred over 25 miles per hour had higher injury severity compared to those lower than that. So those are just examples of some splits. You can go to the next slide. Decision tree only had a ROC of about 68%. You can go to the next slide. So we looked at random forest. This is an ensemble method that basically subsamples different random sampling of rows and features. So it randomizes your data set, and it feeds that to different decision tree learners, and then scales that across hundreds or thousands or even more decision tree learners, and then makes a majority vote for each point. And it's really helpful with nonlinear data sets, and it's pretty robust in terms of reducing overfitting and ruling out outlier effects. And you don't have to tune it as much as you do other models. Next slide. Here's a comparison on what we mentioned earlier with the equal size sampling versus the random forest SMOTE sampling. So you can see highlighted on the left side, we have the true positive and true negative cases fairly equivalent to one another in a high accuracy of 95%, whereas on the equal size sampling, you really only see the majority case has a high accuracy in that portion at the expense of everything else. We also have a lower sample size and a lower accuracy. Go to the next slide. And here's the ROC comparisons. You've got about 99% on the random forest SMOTE. Equal size sampling had about 75%. And the feature importance from the random forest mote was mostly geared towards driver distractions, travel speed, what the driver was doing prior to the crash, such as merging and U-turning, and substance impairment. XGBoost was another ensemble method we looked at. It works similar to gradient boosting by boosting weak learners. However, it's more efficient and scalable than a normal gradient boosting method. It's better for larger data sets and has some built-in regularization features that can reduce overfitting. But basically, it boosts weak learners to learn from different mistakes of previous decision trees to make a more robust prediction. I left out, but the ROC was our second best on that. I think it was around 88, yeah, 90% on that. Thank you. Next, we have numerical models. So these are mathematical methods that predict probabilities of different classifications. And so we looked at artificial neural network, logistic regression. We did attempt to do support vector machines. However, after running it for 2 to 3 days, it still did not reach its convergence. And so we ruled this one out. We did attempt to use we used PCA on it and reduced the feature space to about 22 features, and yeah, still took quite a while. So we ruled that out. But yeah, you can see at the bottom some of the pre-processing steps. You require one-to-many, so one-hot encoding, and then you have to do normalization on the numerical models to bring everything into the same magnitude. Logistic regression is similar to normal regression. However, it's making a classification between a binary and variable. So to do that, it needs to use a sigmoid function and predicts the probability of that. And yeah, the AUC or the ROC on that was 80%. Artificial neural network was the highest performing numerical model. It performed at 84%, and it works similar to brain synapses in the human brain. Basically, you've got the input layer, hidden layer, and the output layer, and the hidden layer has the neurons, which are just weighted numerical values that it learns how to optimize, and you freeze the weights and then can make predictions from there. We looked at several different variable importances. Caleb mentioned we did genetic algorithm for the first filtering, and then here's a random forest learner and a logistic regression that we looked at for variable importance. You see some similar values like vehicle age, impairment with alcohol or drugs. However, you see on logistic regression, vehicle age is one of the #1 variables, and then it makes a lot of designations with the make of the vehicle. So some differences depending on different biases in each model type. Overall, the random forest SMOTE method outperformed everything in terms of accuracy, sensitivity, specificity, and the ROC metric. XGBoost was second, and then as far as numerical methods, the ANN method was the best numerical. And here's just the ROC of those. You see random forest very high. We initially suspected there may be data leakage on this because it's so accurate. We did go back and look through the features. We identified one that did occur post-crash, which was the impact variable. We ruled that out and confirmed no others were any post-crash features. And judging by the fact that the other models don't perform as high, it seems that there's not any more data leakage. Otherwise, you would see everything in the high 90%.
So following the evaluation phase, after we did our modeling and the standard CRISP DM methodology, moved on to deployment. As Chase mentioned in the beginning, deployment for this type of thing, in the CRISP DM process, you can always go back to a previous step. And we think that that's the best way to sort of approach deploying this type of modeling. There's a lot of next steps that could be taken back in model space to just, improve the dimensionality by doing some reduction, doing a little bit of sensitivity analysis on some of the variables, tuning out some of those parameters that were skewing the model in one direction or another, and then just expanding on some of the features that we discovered during modeling and evaluation. As Nathan mentioned, we didn't have the computing resources to get a converging solution with SVM, but that might be something a team would want to look at in the future, reiterating to get to something that could be deployed to industry or to a business use case for automotive manufacturer. Next slide. So a lot of this we've already talked about throughout our presentation. Obviously, we're here to try to take a look at what variables are heavily influencing and predicting the severity of injuries in a car accident using the CRISP DM methodology and the NHTSA data on crashes. We were able to sort of pick up a few things that make sense logically, but it's always great to see the data to back it up. There's a huge importance in vehicles having more safety features, drivers behaving as you would expect them to behave on the road, and the environment and the conditions that the accident took place under. Of all the models we use between the numerical and the categorical, as Nathan mentioned earlier, the random forest with synthetic minority oversampling technique was the most accurate, had the closest sensitivity and specificity to one another, and those were also the largest values. So that was the best model that we developed. Some of the key features that determined a severe injury, like I said before, a lot of these sort of come as common sense, but when you're starting with 200 plus variables in an accident, it's really important to make sure if you're an automotive manufacturer, that you're drilling in on the right things, or if you're a policymaker. And distracted driving, vehicle speed, substance impairment while operating a vehicle, and then certain activities on the roadway that just happen to be more dangerous, like making a U-turn or merging, things like that. We also noted that vehicles less than 5 years old showed a pretty significant reduction in severe injuries compared to older models. If I was a betting man, I'd say that that's probably because we've seen such an advancement in things like collision avoidance, adaptive cruise control, lane keeping, things like that in newer vehicles, and that's probably a likely cause for why we're seeing a reduction in newer models. And moving on to the next chart here, I think that that's something that public policy could probably inform. Typically, you see higher tax rates on newer vehicles as opposed to older vehicles. If you want to go to the next chart, Caleb. Like I said, in public policy, this is one point that came out of our modeling and our evaluation was, there perhaps is an incentive to, try to convince folks to get the older vehicles off the road that don't have the same safety features that newer ones do. Like I said before, it was, over 25% reduction in severe accidents, so that's pretty significant. And then, that type of data also helps automobile manufacturers know what type of features are going to keep their passengers safe. Next steps, I kind of talked about this a little bit before, but deployment at this point, this stage in the game is a little bit beyond the scope of this project. There's still some refinement and more modeling that can be done before it gets deployed into industry. But we were able to learn quite a bit about all the different variables that contribute to injury severity and car crashes. Some recommendation we have are just, dimensionality reduction, as I've already mentioned, sensitivity analysis, and tuning out some of those hyperparameters. That's all we have.